Maintaining rotational equilibrium with mobiles.
There is a mobile M1 that has 3 different masses and another mobile M2 attached to it by a string. M1 is hung from a stable metal rod. M2 has 2 different masses attached to it. All of the masses on both M1 and M2 are set at certain distances from each other. Find out where the string should be attached from the metal rod to M1 and from M1 to M2 in order to establish translational and rotational equilibrium. Assume the strings are weightless. See sketch for distances and mass values. This is a sketch of our problem. As clearly seen, each mass is placed at certain positions from each other and the ends of their respective meter sticks. Notice how the whole mobile system is distinguished into 2 different parts. M1 represents the top mobile and M2 represents the bottom mobile. Here are the mass values for each mass used in this problem. We will use these mass values later on in our mathematical computations. I would like to point out that mass S1 refers to the top meter stick and mass S2 refers to the bottom meter stick. This is the FBD for the top mobile, M1. The only force that acts upwards is the force of tension in string 1. The forces that act downwards are the weights of masses 1, 2, 3, 4, and 5, and the weights of both the top and bottom meter sticks. This is the FBD for the bottom mobile, M2. The only force that acts upwards is the force of the tension in string 2. The forces that act downwards are the weight of mass 4 and 5 and the weight of the bottom meter stick.
Since we know this system has to be in both translational and rotational equilibrium, the net force and the net torque will both equal 0. First off, set the sum of the forces in mobile 1 equal to 0. Make sure the signs are correct. Clockwise is negative and counterclockwise is going to be positive for this problem. Remember that the meter stick attached and all of its other components act as a system. When the force of tension is isolated to one side of the equation, the force of gravity times the sum of the 5 masses and the masses of the 2 meter sticks will be on the other side of the equation.
Now, solving for the level arm of the top string will give the position where the string needs to be hung from the metal rod in order to maintain rotational equilibrium. The first step in solving this problem is to set the axis of rotation at a certain point on the top mobile. So, set the axis of rotation on the 0 meter mark, or the leftmost position on the meter stick. Next, set the net torque equal to 0. Remember to be careful while setting this up. It is very easy to mess up the signs. Also, remember to include the torque of the top spring in the equation as well. Expand the variables to get each object's level arm times each object's force, which will be the object's mass times the force of gravity for all the masses and meter sticks.
Isolate the torque of the top string in order for all the variables to be positive and to be able to solve for the top string's level arm. If you look closer at the equation, notice that the force of gravity can be factored out, so factor it. We are left with the top string's level arm times the top string's tension force equals the force of gravity times level arm and mass of each object. To isolate level arm, divide the top string's tension force on both sides of the equation. Now sub the top string's tension force equation that was solved earlier. Cancel out the force of gravity. Now you have your final equation. Sub in all of your variables to get the answer of 0.57 meters from the axis of rotation. This means that the top string should be placed at the 0.57 meter mark on the top meter stick in order to establish rotational equilibrium. The exact same process applies to the bottom mobile. So first off, set the sum of all the forces in M2 equal to 0. Now isolate the bottom string's tension force to one side, then expand all the other forces on the right side of the equation and factor out the force of gravity.
Solving for the level arm of the bottom string will give the position where the string needs to be attached to the bottom meter stick in order to maintain rotational equilibrium. The first step in solving this problem is to set the axis of rotation on the 0 meter mark, or the leftmost position on the meter stick.
Set the net torque equal to 0. Have all torques on one side of the equation and remember to be careful with the signs. Sub in the torque equation for each torque value. Isolate the torque of the second string to one side of the equation. Divide both sides of the equation by the bottom string's tension force. Now sub in the bottom string's tension force equation that was solved for earlier. Cancel out the force of gravity. Now you have your final equation. Sub in all of the variables to get the answer of 0.5 meters from the axis of rotation. That means that the bottom string should be placed at the 0.5 meter mark on the bottom meter stick in order to establish rotational equilibrium.
Now we are going to test our answers experimentally. In order to set this up in the lab, you will need 2 meter sticks, a string, 2 mask sets, tape, and 3 rods, and 2 holders to connect the rods. Make sure to hang each mask from a specific location on the meter sticks. The green arrows represent the level arms of the top and bottom strings that we just solved for. Once everything is attached and the top mobile is hung with a metal rod, the entire system should be hanging like so, which means that it is in rotational equilibrium. If the mobile is not balanced and in rotational equilibrium, then there is most likely an error in the math.
Because our project was based on solving for the movement arms of the top and bottom strings mathematically, there was really no experimental error. Messing up our mathematical solution would really be the only way for there to be significant difference between the mathematical and experimental solutions.